Good morning. So it is a pleasure to come here and share some of the things what we are doing in our group. So today I'll be mostly focusing on how do we design the software libraries and middleware for Exascale systems. So what are the opportunities and what are the challenges? So many of you might have seen this these slides. So this data is taken from the top 500 list, which compiles all the machines in the top 500 ranking. So here you will see like this line actually shows how the field is moving. That is the number one system in the world as the year progresses. So here you will see that now we have the Tihanhe-2, which is the 33.86 petaflop system. And then this line actually shows the bottommost, like the 500th machine which is on the list. So that also you will see that over the years even the lowest powerful machine is also growing, and then this has the cumulative power of all the 500 machines. Now obviously there is the next goal is to reach 100 petaflops, and people are thinking that a lot of different countries are working to reach this goal. Might be by next year. You will see like some 100 petaflops machine might be coming up. And then of course the goal is to go towards exaflop, and when this exaflop and the Exascale study started like 2010, the original goal was to actually achieve in 2018. But broadly people are feeling that we will not be able to have an Exascale system in 2018, but the realistic goal is to have it in 2020 or 2022. So that is the kind of time frame people are thinking where an exaflop system will be coming up. So when we are designing these machines, obviously there are two different directions which are evolving. The first one is of course the scientific computing. Many of you must be familiar with like the message passing interface, MPI, including MPI and OpenMP has been the dominant programming models, but there has been a lot of discussions taking place towards partitioned global address space, or called PGAS, and that is what I will be also focusing a little bit later. But the entire new thing which is coming is this big data. So some of you must have heard about that, and so here the focus is on large data and data analysis, the Hadoop, which is the most common one which is emerging, and at the same time there is a newer middleware which is coming as Spark to carry out in memory computing, and also the Memcached which is also being used for Web 2.0. So both these directions actually has an importance in driving these Exascale systems for the next decade, and I will try to bring some of the challenges whatever is involved in this domain. So now let us take a look at the top 500 systems, how they are emerging over the years, and this one shows like a very nice trend what happened in like the very old days, let us say 1996, 98 kind of things. All the top 500 machines were very large scale system, like these were proprietary systems from IBM, from Cray, SGI kind of things. But then over the years the commodity clusters entered the market. So when I say commodity clusters, I mean these are like typically you buy the servers, you buy some commodity networks and then put them together. And over the years you will see now we are almost like 83 to 85% of the top 500 systems are clusters. Okay, so these are not proprietary systems, these are commodity systems. Okay, and that is helping a lot to get us into this top 500 machines or very powerful machines over the last decade. So what is happening, if you see a lot of this modern HPC cluster architecture, there are a few ingredients here. So of course the first one is multi-core processors. So that we have seen for the last several years. The multi-core processors era is evolving very strongly. These days you get all the latest, let us say Ivy Bridge, you get like 10 cores, 12 cores per socket. So per node you can get up to even 20 cores. And then of course the high performance interconnect, we will be talking a lot today about the InfiniBand, the new RDMA or remote DMA mechanisms, and these mechanisms are able to give us like let us say less than 1 microsecond latency and also like more than 100 gigabits per second bandwidth. So this is what you can get in the commodity manner. And the third thing which is helping also is these accelerators or co-processors, both from the NVIDIA side, the GPGPUs, and also from the Intel. We'll be talking about the many integrated core or MIC. So these are the ingredients or the hardware components which are helping us to design these large scale systems. So if you see like all these Tiahane 2, Titan, Stampede, Tiahane 1A, all of these systems have these kind of 3 components in common. So if you take a look at like what is happening on the InfiniBand and then the clusters, so here you will see that these are from the November 2000 top 500 list. Next month again we will have a new list at the ISC in Germany. So now we have like around 207 IB clusters, almost 41% of the top 500 clusters use InfiniBand. And just if you see even the top 40, almost half of them use InfiniBand. The largest one is at the TAC, which is the Texas Advanced Computing Center. This has almost like 500,000 cores, and this has both like the Intel, the regular cores, as well as the many integrated cores or the MIC connected with InfiniBand. So that is the largest open science research cluster available outside. And then of course we have all these other kinds of clusters are being deployed all over the world. Okay, so you will see that this shows the power of the commodity clusters, how things are evolving. So if we take a current look, and then now let's take a look at Exascale, what people are trying to propose. So this one is this data has been taken from Professor Jack Dangara. So what he did here, let's say this is take like 2014, the current year, and let's take a reference machine which is the Tiahane 2A, and then let's try to see like what are the characteristics of this machine in terms of system peak, power, memory, node performance, node concurrency, etc. And then let's take a look at the goal what we have for the Exascale system like 2020 to 2022, and then this column shows what is the gap, and that is the gap we need to actually bridge to design this Exascale system. So if you take some of the like compare along the rows, so here you will see like current machines are 55 petaflops per second, and we are trying to aim for exaflop. So we need almost like factor of 20 improvement in the next 6 to 7 years. Now at the same time you will see the power, currently this machine is taking 18 megawatt, and the Exascale system the target is 20 megawatt. So we want to almost remain the same power, but try to improve the performance by a factor of 20, and that is a big challenge. Okay. And similarly you can compare here like let's say system memory, we have petabytes, we want to go to 32 to 64 petabytes, so we need an improvement of 50x. The node performance, that means within the node, a single node, so here you will see like we get around 3.43 teraflops per second. In fact, here if you see the breakup, here it comes only 0.4 teraflop comes from the CPU, but the most of the 3 teraflops come from the coprocessor, which are the Intel MIC. So you will see the trend is changing like this many integrated core accelerators will be giving us much more power in terms of the compute capability than the regular host. And then if you see like the node concurrency, that means within a single node currently we have 24 CPU cores and 171 coprocessors, and for the exaflop systems we need almost 1000 or 10,000 of these things happening in a single node, and there we will see the improvement we need almost like a factor of 5 to 50. Then if you think of the networking, what we will be talking today a lot, here you will see only like 6 gigabytes per second, and we want to go to almost 200 to 400 gigabytes per second, the data which is coming out from the node going out and coming in, and that takes around like factor of 40 to 60. And similarly system size, currently we have 16,000, and people imagine like having these systems we will have 100,000 of these or 1 million of these nodes. So how do you design the networks? How do you design the protocols, the routing, the topology for all these kind of systems? So that is a big challenge. And then you will see the total concurrency. That means how many processes or how many threads you can run on these machines. Currently you can have 3.12 million processes. Then if you take like we have the Intel MIC, it has 4 threads per core, so you can run like 12.48 million threads. and people are imagining the Exascale system will have billions of threads, okay? And that is for latency hiding, because the way the systems will evolve, as many of you might have seen, it's called memory wall. So that means the more farther you go from the CPU, it takes more time to get the data. So that means you need to have enough threads to initiate the operations, so that you are trying to basically hide the latency. Otherwise, you will not be able to get the speed up. So this is the kind of at one end, if you see that these are very challenging, but at the same time, if you see from the community point of view, this challenge makes a lot of sense. So this is where the field is moving, and just like over the years we have gone from like gigaflops to petaflops to multi-petaflops, I am sure in the next 6-7 years we'll hit the exaflop. So that is the broad goal, what I'd like you to keep in mind, but now let's go into some different components and see how things are evolving. So one of the important things when you design the system is of course the programming model. How do you program these systems? And traditionally there has been, like let's say very old days, it used to be shared memory. That means it is cache coherent shared memory, and as many of you might be knowing, you can only do it within a node, but you cannot do it across the node. It is a big challenge. There are some products out there which goes up to certain number of nodes, but you cannot have a like this kind of large system to have shared memory, cache coherent shared memory across all the nodes. So in that context, mostly the distributed memory or MPI, which stands for message passing interface, has been the dominant programming model. So all these machines currently use that. Now looking forward, people are moving into this partitioned global address space. We'll talk a little bit more about this later on. But the idea is to take all this logical shared memory and then put them together. I mean individual memory on each node, but you try to come up with an abstract which is a logical shared memory. So if you can do that, then there are a lot of activities are taking place like global arrays, UPC, Chapel, OpenSHMEM, X10. So that's what I'll also talk a little bit later about these things. So first of all, then if the MPI is the most prominent programming model and people are looking at the Exascale, so the question is how do you bring Exascale into the MPI, or how MPI plans to meet the Exascale challenges. So of course the power requirement, as I indicated, that is the biggest challenge, and the power requirements actually comes from the data movement. Okay. So the question is what we can do to minimize the data movement operations, and in order to do that, actually the MPI forum, which is the standard body for the message passing interface, which consists of a lot of academia, industry, national labs. So they have been dealing with all these things over the last several years. So there are a lot of discussions taking place, like to have non-blocking collectives. For example, let's say you are trying to do a broadcast, or you are trying to do an all-to-all. The MPI standard currently has only blocking collectives. So that means if you initiate an all-to-all, the processors are just polling. They don't come out of it until it finishes, and this is where you consume power and you lose time. So the question is, can we do them non-blocking? So that means you initiate the operation all-to-all, but if you have computation, you proceed, and then later on you come back and try to see that if the operation has been finished. Okay, so in that case you can actually overlap computation and communication. So in fact in the next slide I will show the latest MPI 3 standard actually introduced this already. Non-blocking collectives are there, and different MPI stacks have already provided support for this. So you should be able to go ahead and then experiment with this kind of newer primitives for your systems. The same thing is happening for called one-sided interface. So that means earlier the MPI used to be two-sided, like send and receive. I send, you receive. So that means you need to have synchronization between both the processes in order to have the data exchange. But nowadays the new semantics is to have one-sided interface, and that also reduces synchronization of the sender side and the receiver side, and it also allows overlap of computation with data. So that means let's say I might be computing, and through remote memory access or RMA you send me the data which is coming to my memory, and I don't have to be involved. And when I finish my current operation, I go and check if the data is available and then proceed. So that also gives overlap of computation and communication. And then to manage this concurrency, I indicated like people are looking for billions of threads. So in that context, people are trying to think of this partitioned global address space, and there are various models here. I'll talk about that in the next few slides. So people want to do hybrid programming. So this hybrid is not from accelerator side, but hybrid from programming model side. So that means you can combine MPI with, let's say, OpenSHMEM or MPI with UPC, okay? So that you can take advantage of both message passing as well as of this logical shared memory or the partitioned global address space. And of course, the resiliency has been a big challenge, because as we are putting these large scale systems, how do you achieve fault tolerance, how do you achieve resiliency, always is a big challenge. And there has been a lot of discussions taking place. In fact, for MPI 3 forum, a lot of ideas were proposed in the last several years, but none of them was a winner. So that's why MPI 3 standard didn't have any support for MPI fault tolerance. But the discussion is still continuing, and we expect like might be in the next MPI 3.2 or MPI 4.0, you will actually see some of this support for fault tolerance. So the MPI 3, which was introduced 2 years back at the SC 2012, so they have actually provided this kind of non-blocking collectives and then improved one-sided RMA model. They also have introduced things called MPI tools interface, and this is also becoming a big challenge as the systems are becoming more complex. So let's say you as an application writer are trying to write your application and you don't get performance, but the question is, where does the time go? Of course, there are a lot of tools, but the tools so far has been written on top of MPI. They don't have a lot of knowledge what is happening inside the MPI. So this MPI tools interface actually allows to expose a lot of internal variables of MPI to this MPI tools interface, so that any tools can actually take advantage of that. Okay? For example, if you, let's say, MPI has some different algorithms, collective algorithms for different message size, system sizes, you make those changes. You can actually see it from the tools layer that this is exactly is happening. Now the algorithm 1 is used or 2 is used, then you can do an analysis saying, no, for this system size or message size, algorithm 2 might not be good, we should switch to algorithm 4, then you will get. So these kind of interactions you can do and then try to get the best performance out of your system. So now let's take a look at a little bit on the PGAS side. So as I indicated, the key features are like simple shared memory abstraction and to carry out lightweight one-sided communication, and the focus is to really express irregular communication. If you would have written some applications, you will see that the typical scientific applications fall into two broad categories, where there is a regular communication. So that means you exactly know, like I am sending it to some neighbors or some stencil computation or 3D, 4D, those are like regular. But there are a lot of irregular applications, okay, so where what happens is based on the data and which node it is, you are trying to take some actions, and those are very hard to write in MPI. People have done it, but it takes lots of effort to convert that into MPI, and even though you convert into MPI, many times you go through load imbalance, so that you don't get good speed up. And this is where these PGAS models are coming to help, and I will show you some examples, concrete examples later on, how you can actually exploit these kind of features in the PGAS to get very good performance. So in that context, there are different approaches are happening, like on the language side, these are like support from the compiler, there are a lot of work going on. I will touch a little bit about UPC. Similarly, from the library side, there are also different solutions are coming up, and I will touch a little bit about OpenSHMEM. Okay, so just for the sake of time, I will just take only two, but there are a lot of actions are taking place from all these domains, and then we will see in the next few years, we will find out which ones actually will win and then move forward. Okay. So this is the concept I was telling, like how you can combine MPI and PGAS. So the broad idea is that in the next generation systems, you will see it will be hierarchical. That means we are already seeing that. Currently, if you see, we have a socket. So the cores are within the sockets. There are multiple sockets within the node, multiple nodes within a blade, multiple blades within a rack, then multiple racks connecting to the switches. So these are kind of different hierarchical things are happening, and in that context, so the question is like, can we do MPI across some address spaces and PGAS within an address space? Okay. So the idea is that MPI has been good at moving data between address spaces, but within an address space, MPI can interoperate with other shared memory programming models, and these can also coexist with the OpenMP like people write MPI plus OpenMP applications. So through OpenMP primitives, you can actually offload the computation or through multiple threads. So all these things can actually coexist. And so if your applications have different kernels with different communication pattern, so you can try to mix and match. So that is the kind of a goal people are aiming for. The other angle is that with this newer kind of programming models, so the question is, should people rewrite the complete applications? If you can, you are welcome, but it is a huge effort, because over the years a lot of these applications have been written. Let's say 30, 40 years of effort, it will require another 30 or 40 years of effort to rewrite all of them. That is not a good solution. So what people are proposing is to port critical kernels to the desired model. Okay. So what does that mean? So if you think of, let's say there is an application, and here you, let's say you have different kernels, and you see that because this application may have regular communication, may have irregular, both of them can coexist, and let's say you see that some particular, like these kernels, let's say this one like 2 and some n, they are not scaling. Okay. But on the other hand, let's say these are scaling. So now the question is, can we change these two kernels to something else, like let's say PGAS? Okay. So you don't have to totally rewrite the application, you just write only some portion of that application where you don't get the scalability. And in that way, you can actually get the best of distributed computing model and best of shared memory compute model, and this is what exactly the Exascale roadmap, if you read this big article, here it says like the hybrid programming is a practical way to program Exascale systems. And I will show some examples in our group. We have done some of these studies. I will show the results. You can actually combine MPI with OpenSHMEM, MPI with UPC, and suddenly you see very good speed up, which you cannot get from either MPI or let's say OpenSHMEM. So that brings us to the bigger challenge, like we see all these commodities, components are coming up, different programming models are coming up, then the different kinds of applications. So how do we put it together? So if we take a look at the overall challenge, so this is what I see at the bottom layer. We have all these components like multi-core, many-core architecture, different networking technologies, and different accelerators. Then at the top, we have the application kernels or applications. So that means we need to deliver all this performance and scalability to this layer. And what does that mean? So that means these are written with some middleware, or these are written with some programming models. Okay, that's what we discussed. Like the applications are written in this manner. It could be MPI, PGAS, CUDA, OpenSCC, Silk. Even for big data, we will introduce a little bit later, like Hadoop, MapReduce, etc. So that means we need to take all this performance and deliver to this layer. And if we can deliver, then of course the applications can be can actually exploit all these features to get the performance and scalability. And that leads to, this is where the communication library or runtime fits in. Okay. So it could be like different kinds of MPI libraries, different kinds of runtimes for PGAS, or a combination of MPI and PGAS. And internal to that, you will see like the challenges are how best to provide point-to-point communication, like let's say one-sided, two-sided, how do you design collective, synchronization, I/O file system, fault tolerance. So all these things are the research challenges. And once you have these solutions, then they get integrated together and is available to you as a runtime or a library, and then people can try to take advantage of that in the applications. But then what is happening, as we see these modern systems are being so complicated, you cannot just do a design at one layer, okay, because it has dependencies across the other layers. So this is where a lot of discussions taking place to do co-designing. So that means you may need to modify something at the runtime or modify something at the programming model, and they need to work together, or even take advantage of that into the hardware level, so that the hardware provides some primitives and then you take advantage of this. So a lot of this co-designing is taking place in the community to actually aim for performance, scalability, and fault resilience. So those are the three goals people are trying to work on. So what I'll do in the next part of the presentation, I'll take some of the examples and seeing how the community is working on these, and give you some very concrete performance data. Okay. So if somebody asks at a very high level, people are talking about this model. I introduced MPI and PGAS. Of course, within the PGAS, there are all these choices are there. Nobody knows which one will win. So people are calling in a general saying, yes, people believe that it will be MPI plus X. But what will be that X? Nobody knows. We'll see out of in the next few years, it'll get converged. But if you want to come up with a wish list saying, okay, how do we design this MPI plus X at Exascale, you will come up with this kind of a list. Okay, so the first of course is the scalability. You want to achieve 2 million or billion processes. So that means you need very highly efficient inter-node communication, intra-node communication, both two-sided and one-sided. Okay, so that is the biggest challenge. Then after that, this is also becoming very important to have extremely minimum memory footprint. As the systems are becoming large, if some of you know, like to design a library runtime, we use a lot of buffers, descriptors and all those things. But at the same time, with all these, let's say many integrated core, if you take like the Intel MIC, you get very little memory per process or per thread, and that will continue to go down. Okay? So the question is, we cannot afford to write a library or a runtime with a huge memory footprint. Then the applications will have very little space to work on. So this is becoming a challenge. Then how do you balance intra-node and inter-node communication? As I indicated earlier, within a node, people are expecting like a 1000 cores or even 10,000 cores. So you need to balance both the sides, good communication within the node and also good communication outside or to and from the node. Then of course, there is a efficient multi-threading is becoming more important. Then these accelerators, and then this collective communication. There is a lot of work taking place, so like how do you take advantage of offload. These non-blocking collectives are introduced, topology aware, power aware, then fault tolerance, resiliency, QoS support, and then these hybrid programming models. So those are the kind of very broad challenges the community is working on at all different directions. So in addition to that, there is a cross-layer approach. I talked about this extreme low memory footprint that is happening, but then this is something new. People are feeling that as the machines are being complicated, earlier all these libraries or runtimes used to be only static. They never used to take a lot of information. But just like you know, I mean, let's say Sao Paulo, I mean, so just to give you an idea, I mean, all this traffic jam takes place, right? So every day you people adapt, okay, saying where the traffic jam is occurring, how do you get around with it. The same things we need to do at the systems level. So I call it like a DLA framework, so that means discover. So any library or runtime need to discover saying what is the overall network topology, what is happening network topology for processes for a given job, what is the node architecture, health of the network and node. Okay. So as soon as you run some jobs, it has to discover saying where it is running. Okay. And once you discover, then you need to learn. Okay. Saying over like if this application is running for multiple times, so then you see, okay, what is affecting the performance and the performance and the scalability, what is the potential for failure, and based on that, then you need to adapt. So that means that the library itself or the runtime need to change its internal protocols and algorithms, the process mapping, fault tolerant solutions, so that when you run these jobs over and over, you will see better and better performance from that system. Okay. So it cannot be just that you just run a library or an application and it just takes only information once and then tries to do the best. You cannot do that. And all these things you need to do with a low overhead techniques, because as you know, this discover, learn, adapt always has some overhead. Okay. And these are only good for long running applications. I mean, if you have very grand challenge applications which are running on the systems for let's say 1 week or 2 weeks, you want to run these applications, even if you spend some time on this DLA methodology, it is good. In the end, you will see the benefits. But if you are trying to run this for only 15 seconds, then of course this is not good. Okay. But there are a lot of applications out there which are really running for over a lot of time. And it may not be your end application. It can be only some particular libraries. So think of like a Fluent. I mean, as you know, the Fluent is a ISV, and a lot of people use Fluent. So if you can optimize something at the Fluent layer, you will see you will have impact on a lot of applications. So same thing with the MPI library. A lot of people use the MPI libraries. If you do enhancements within the MPI libraries, it gets translated to all these upper layer, the ISVs and end applications. So in that context, I'll try to go into much more concrete things. We have been in my group have been working on this project. Some of you might be knowing or even using it. We started this work on the MPI libraries even on the 2001 when the InfiniBand had started coming. And over the years we have this the MVAPICH project. So there are different versions. We started with MPI 1, then we moved to the latest one, supports MPI 3. Then even since 2 years back we have this hybrid version, support for GPGPUs and MIC. So currently is being used by more than 2000 organizations in 72 countries. It is an open source, and it is actually empowering a lot of top 500 clusters. So as I mentioned, this is the 7th ranked tax system with 500,000 cores. So we have taken this as a project from a university, and it is actually running in a production environment with 500,000 cores. And similarly, it is also running on all the Subami, NASA PlayDAS, Kinland, a lot of other these systems. So I'll try to bring some very concrete numbers and the designs, what we have done or what we are doing to match with all these objectives. Okay. So in fact, yesterday night we actually made a release. Some of you who are on our mailing list might have seen this. So we are trying to finalize this MVAPICH2 2.0. So in fact, there are a lot of good features here. I talked about this RDMA optimization, this is the remote memory access. So we had the support earlier, but now we have optimized it further. We have provided this MPI support, and also there is a cross memory attached support. I'll talk in the next few slides. So please feel free to use this latest version. Now let's go into only some points. We will not have time to go over all those points, so I just selected a few points to give you an insight. But if you have any questions, I am here throughout the day. I'll be happy to discuss with you. So what I'll try to talk first, how do you achieve scalability, both for like the internode, intranode, and then this memory footprint. I'll talk a little bit about GPGPUs, MICs, fault tolerance, and then the hybrid programming. So this chart actually shows what is happening in this InfiniBand field over the years. As some of you might be knowing, there are all different kinds of adapters, both from Mellanox as well as from QLogic. So these are all different adapter combinations starting from DDR, QDR. This is the PCI Express Gen 2, PCI Express Gen 3 with Sandy Bridge and Ivy Bridge. So you will see that this chart is trying to show what is happening to the small message latency. So it's like half of the round trip. And over the years, it is steadily dropping. So now you will see that almost we get 1 microsecond or a little bit less than 1 microsecond to do MPI communication from one node to the other node. So it goes through from the processor, goes through the adapter, the switch, the other side of the adapter, and to the memory. Okay. And then the right hand side is the large message latency, and of course the one which has a higher bandwidth wins. So if you take the very latest combination of Ivy Bridge processes and Connect IB dual FDR, you will see the best performance. Then these are trying to show in terms of bandwidth. Okay, the bandwidth is the rate at which we can pump data from single node to the other node. So here if you see, as the message size increases, so these are all different adapters, and then this is the one which is the Ivy Bridge together with Connect IB dual FDR, we get almost 12.8 gigabytes per second. Okay. Sorry, gigabytes per second, and if you multiply by 8, so it's effectively 100 gigabits per second. That's what we are getting with this commodity hardware. And then this is the bidirectional bandwidth, so that means both the sides are talking to each other, and there we get almost like 24.7 or 25 gigabytes per second, so 200 gigabits per second. Okay, so this is the powerfulness of this commodity network, where you can actually achieve these days 100 gigabits or unidirectional or 200 gigabits bidirectional. Now that is over the network, but as I mentioned, when you try to design this kind of library, you also need to focus on what is happening intranode. Okay, because as the nodes are becoming larger, a lot of communication take place within the node. So if you don't optimize that, you will not get the speed up. So over the years, we have been also continuously trying to optimize all these intranode. Every few years we come up with some new design. So we are almost in the 5th generation of that design. So here you will see, like, this is the Intel Ivy Bridge system. Within a socket, we can actually give you MPI latency of 180 nanoseconds. Okay, so that means within the socket, different two cores are talking to each other So we deliver latency of only 180 nanoseconds. When you go across the sockets, it is around 415 nanoseconds. Now that is with respect to latency. Then with respect to bandwidth, let's say you are trying to do a lot of large message transfer. If you standardly go through the shared memory, you don't get very good performance because you are trying to do two-sided, like I am trying to write, somebody else is reading. So we have a lot of one-sided design. One design we had earlier, which is a kernel module called LIMIC, and now actually over the years, many of these features have come to the standard Linux called a CMA or a cross memory attach. Okay. So these days you can directly make those calls, and that's what I indicated in our release we have supported. So here you will see that for large messages, this CMA support actually gives you much more significant benefit in terms of the latency and bandwidth. So if you have any of such newer clusters, you should turn on those CMA support or even the LIMIC support, and you will see your performance of the applications going up. So then this shows the new MPI3 RMA, or the remote memory access operation, and here you will see similar kind of things like a get and put. We can give you like around 1.56, 2.04 microseconds, and bandwidth wise we saturate the link. And then also intra-socket, you see this is like just 8 nanoseconds. That kind of performance we can give with the newer kind of RMA semantics. So if your applications you can rewrite using this one-sided semantics, you should be seeing very good performance here. Now, so those are the basic performance. Now how about the memory footprint we talked about earlier. So here you will see again over the years what is happening is like InfiniBand is also, the standard is also trying to provide some of these things. The common one, if many of you know, called RC, which is reliable connection, that takes more memory. Then few years back, one extended RC, extended reliable connection, was introduced, XRC, and that's what it shows. Like the same library, the memory megabytes per process, you will see suddenly will drop if you have XRC support. So that means if you have an application, if you multi-core environment, you should turn on your XRC support, and then here you will see that the performance remains the same, or sometimes even you win a little bit and gain a lot in the memory footprint. Then in terms of that adaptivity, what also we have done is, let's say you have these different modes like unreliable datagram or reliable connection. So just like having a car which is like a hybrid car trying to run on gas and the electric, the same thing we have done in our MVAPICH2 stack. There is an hybrid mode. What it does is it internally tries to monitor. When you are trying to run an application, it tries to monitor who is talking to whom, and based on that it selects whether I should do RC or I should do UD. Okay, and you don't have to change anything. Of course, there are a lot of parameters so you can tune to match with the application characteristics, but here you will see that just like using few commands like this, you should be able to see always your hybrid is trying to do equal or better than the other modes. So once again, if you have large scale systems, you should be using these kind of modes to get the best performance as well as reduced memory footprint. So those are like some sample things. So let's go into the accelerators domains. There is a lot of actions taking place. So first I'll talk about the GPGPUs, and then I'll go into the Intel MIC. Now especially on the GPGPU side, there are a lot of actions taking place. Few years back, in fact, if you want, so this is like this is the GPU memory, this is the CPU memory, and then this is the InfiniBand. If you want to send some data, earlier what used to happen, that this is the very initial things, you need to take the data to the memory, within the memory you copy and then you send. So that used to be very painful in terms of like latency, so it had very low performance and low productivity. So then after CUDA 4, there was a Mellanox and NVIDIA had this the together called GPU Direct. Okay, it is not a GPU Direct RDMA, so that is the third solution. So here you can do a single registration, so that means data goes here and then you still can make copies. And that is the time actually we introduced something called a CUDA over MPI. So that means earlier people used to do CUDA copy, then do MPI send, the other side MPI receive, and then CUDA. We actually took all these CUDA calls within an MPI stack. So we made CUDA aware so that the end user doesn't have to touch even CUDA. everything happens within MPI, and just like you send MPI send receive from host memory, you can actually do from GPU memory, and everything else the library is trying to do. So that led to high performance and high productivity. And very recently, since last year, this new GPU direct RDMA is happening. So that is again a joint work between Mellanox and NVIDIA. You can actually take the data and directly take it to the InfiniBand. Okay? And that is the support. I will talk into a little bit more details. Even though it looks easy, there are some issues, and we need to resolve it. So what has happened over the last several years in our MPI stack, if some of you might be using, so we have taken always, like every time we make a release, we also take the newer features of the GPGPUs and all these paths into account, so that we provide high performance RDMA based communication between GPU to GPU, GPU to host, host to GPU. We also take care of intra-node point-to-point communication. We also take CUDA IPC, and based on these we also optimize and tune collectives as well as the data type support. Now recently this with GPU direct RDMA, now even though, so let us say you can send data directly back and forth, but if you take some measurements, you will see there are some different things are happening. Okay. So for example, here if you see, this is the green line, like reading from IB adapter and trying to write into the GPU memory, you get very good speed up, the bandwidth. This is Sandy Bridge, this is IB Bridge, you get 5.2 gigabytes per second and 6.4. But on the other hand, if you do the read, is very pathetic. Okay. And that has nothing to do with the problem with IB or GPUs, it is the problem with Intel chipset. Okay. And it has been there for some time. So it was there in the Sandy Bridge, it has been improved a little bit on the IB Bridge, but still you will see there are differences. So in order to bridge this gap, so what we have done is we have proposed a hybrid solution. So that means for some message range, we actually take data here, like reading the data, we take it here, but when you are trying to take it from GPU to InfiniBand, we actually take it through the host and then push it. Okay, so that we can get the performance in both ends, and that is the hybrid design we have. So if you see this performance, so these are the support we provided since supercomputing last year, and we are continuously improving it. So here you will see that this is the standard, like the latency people used to get. So now we have reduced to almost 5 microseconds, the GPU to GPU. Earlier it used to be like around 15-18 microseconds. With the GPU direct RDMA, it improves in the short message latency, and then if you see the bandwidth, this is the small message bandwidth. For intermediate message size, we can give almost by a factor of 5 improvement. And then here again we give around 9.8 gigabytes per second, and bidirectional bandwidth we give around 4.3x improvement. And then here you can see, if you combine InfiniBand together with the Connect IB, which has dual adapters, dual ports, we can almost go to 19 gigabytes per second. Okay, so that to match the both way data transfer. And so that is in the release. Very recently we have been working, this will coming out in the next 2-3 days, not 2-3 days, actually 2 weeks. So here we have actually taken MPI 3 support for GPUs. Like if you want to do like put or get from GPU buffer to GPU buffer, and see this number, less than 2 microseconds. Okay, so we can do actually put with plus from one GPU buffer to the other GPU buffer using GPU direct RDMA in less than 2 microseconds. So this is the best numbers, like in the community, nobody has gone to that kind of low numbers. And at the same time, we also increase the message rate significantly with the new primitives. So we did some evaluation at like a communication kernel level evaluation, like a 3D application and all to all. We actually, this is like the two-sided, this is the one-sided. So we rewrote these benchmarks to see what is the potential benefits of these at an application level, and here you will see like you can get almost 42% improvement or 50% improvement by changing your application from two-sided to one-sided. So in fact, this version is already available. If you have not experimented with GDR, please feel free to download. Of course, it needs all these different kinds of combinations from Mellanox, OFED, NVIDIA and all, and this has actually been GA'd from the Mellanox side. And we are trying to provide all these additional optimizations. In another 2 weeks, you will see a new release coming out. And then also on the June 5th, there is a webinar taking place, Mellanox and NVIDIA. I'll also be talking there. So if you have time on the June 5th, just monitor for that webinar and then please join that to get additional information here. So now so that is happening on the GPGPU side, and as we know, we also have the Intel MIC is coming from the different angle. So let's see what are the challenges there and how do we bring that into the MPI stack. So as some of you might be knowing, the Intel MIC architecture tries to provide you a lot of combinations. So let's say this is your GN and this is the GN5, you can do host only, you can do offload, or you can do the symmetric. That is the biggest challenge. That means your MPI application running on the host as well as on the GN5. And then the final one is the coprocessor. So that means your MPI program only runs on the mic processes. They don't, the hosts, they don't run any MPI program. Now if you try to understand the complexity in these kind of designs, you will see that this is an animation which shows all different paths you need to optimize. So that means where MPI processes can run on the CPU, on the mic, across. So all these paths are there. I'll just very quickly go over like intra-socket, inter-socket, internode, intra-mic. So like this, there are 11 possible paths in a system. So that means if you really want to design a good MPI library, you need to optimize all these 11 paths. Okay. That is just for point to point. The same thing happens for RDMA. Then you go about collectives, it's a nightmare, okay? Because all these different patterns are happening, how do you come up with the collectives? So this is a really big challenge. The community will see how to come up with this kind of a library. So we have done some initial results here. We have published also a lot of papers. In fact, we have put together a code base. It is actually running at the TAC Stampede for some advanced users. It has not been made release. We have plans to do it in the next month. So I'll just try to show some simple sample numbers like internode communication and symmetric mode. So here again the same kind of issues comes like what we saw, let's say the Intel provides this IB verb based communication. You don't need any porting effort, any MPI library will run, but the question is, are you getting performance out of that? So here the same things you will see that when you are trying to do the reading from the mic through InfiniBand, you will see this is like on the Sandy breeze and this is on the Ivy breeze. That is not good, and the inter socket, in fact, it goes down significantly. So here you will see only 370 megabytes, 247 megabytes. These are very low numbers if you are communicating across the QPI. Okay. So people actually deploy these kind of systems saying, oh, I have 2 PCIs, I'll plug into to Intel mic, but see this kind of performance you will get. Okay. So what we have done is again those kind of hybrid designs, what I mentioned earlier, GPUs, here we call something like a proxy. So that means we take help from the host to do some of these communications. Now here if you see, this is like the standard MVAPICH2 and this is the MVAPICH2 mic version, you will see we can improve significantly on the latency and push the bandwidth to the IB speed. Okay. And then same thing also happens like this is inter-socket, similar kind of things what we can do by using this hybrid design instead of just, if you just try to run our basic library, the red lines you will see, those are not good. Okay. But with advanced designs, we can give you better performance. And here it shows like some application numbers using the new optimized, the new mic version. You will see these are like 3D stencil, P3D FFT, we can give you benefits. Now the collectives, again as I said, it's a nightmare, but we have started working on this. We just last week we presented a paper at IPDPS. So here it says again like let's say this is an all gather and all to all. So we take these architectures and the different data paths into account and try to minimize. We don't try to touch the expensive paths, and then we try to touch the paths which are better. And in this way you can see that let's say this is a 32 node all to all, 8 host and 8 mic. So that means we have 32 nodes, and each node symmetric mode we are running 8 processes on host and 8 processes on the mic. So it is 16 times 32, 512 process job. So here you will see like we can improve by 55%, 76%, 58%, and even if you run P3D FFT, those kind of benefits you see with the new collective design. So now let me touch a little bit about the fault tolerance, and then I'll go into the hybrid. So fault tolerance is also making a big challenge. So over the years, we are trying to address that issue. Of course, the basic thing is to have some kind of a checkpoint and process migration. We have that, but people are trying to move into some of the very high performance systems, like something called a scalable checkpoint restart, SCR support from Lawrence Livermore Lab, and now we have integrated that into our stack, so that you can actually do application level, application guided or application transparent checkpointing support. So here it shows some examples, like if you just do basic checkpoint restart, of course it takes a lot of time. We have scheme called migration. So that means if you detect faults or if you are about to fail, you can actually migrate processes from your to be failed node to the one of the spare nodes. You can do that. But the more important is, like, this is the multi-level checkpointing with scalable SCR from Lawrence Livermore Lab. So they have a different ways where you put your copy of the checkpoint. You can do local, you can do a partner, you can do a XOR, or you can do a stable storage. So they have these different schemes, and based on the desired fault tolerance, you can select one of these schemes which matches with your system or environment or application. So we have actually integrated these. So here you will see that this is an example we took, like this is a MPI application, 512 MPI processes. It has almost 51 gigabytes of data in the checkpoint. If you do a very naive way, this is what it takes the checkpoint time. But if you do with the SCR support, either local, partner, or XOR, you significantly cut down the time. And then this is a NJO application we run. It has like a 12.8 gigabytes of checkpoint, and again you can see, like, this checkpoint IO, which takes the most of the time, we can significantly cut it down with this SCR level of support. So these are the kind of schemes you need to adopt if you have very large scale systems and want to have fault tolerance. So then let me touch this hybrid MPI and PGAS I indicated earlier. So this we have been working almost for last 3 years. So we have a separate enhanced package, we call it MVAPICH2-X, standing for that MPI+X paradigm. So it has actually an integrated support. So not only you can run MPI jobs, you can also run pure UPC jobs or OpenSHMEM jobs or any of these combinations. So this package will allow you to experiment with all different programming models, all different combinations, and see which tries to give you the best performance. And we have a unified runtime which actually tries to give the best to all these programming models, okay? So that you can really see the benefits from different places. So here there are some sample numbers, just like let's say OpenSHMEM collectives. Here you will see, like, we are comparing with our version, with there is a scalable SHMEM. There is also OpenMPI has a OpenSHMEM version, so we are comparing. So these are all the latest release. We have the support. You will see we are able to significantly enhance the collective performance. Here there are some even applications. So this is an OpenSHMEM applications. Here you will see compared to all these different libraries. So this is the MVAPICH2-X shared memory with OpenSHMEM can give you the best performance. Now, so that is individually. I just showed OpenSHMEM. Similarly, you can also get the performance with UPC. But now the question is, how do we combine this? Okay. So this is an hybrid. We worked on a Graph 500. Many of you know, like, Graph 500 has a lot of irregular communication. So what we started with an MPI program. So if you will see here, there are 3 different programs available in the MPI world, but none of them were scaling. And then what we did is, this is an hybrid MPI and OpenSHMEM we took, and this is the run on 16,000 processes on the TAG Stampede, and you see we can give you almost 13x improvement. Even compared to the best MPI design, we can give you almost 1.5x improvement. So that shows how you can take advantage of both regular and irregular communication, and here it shows like strong scalability as well as weak scalability. And recently we have done the similar kind of thing called sort. Sort is a very common application people use, and the same thing also happens compared to pure MPI. The hybrid design, you get almost like 51% or 55% benefit. So these are some illustrative examples which actually shows that, look, if you try to combine both MPI and OpenSHMEM, you should be able to actually get this kind of benefits, MPI, UPC. So choose your favorite X and then work together with MPI and you will see these kind of benefits. So looking forward along this direction, of course, there are a lot of these challenges. We are continuously working. There is you must have heard of Mellanox has something called a dynamically connected transport that is coming as the next transport to minimize the memory footprint. We have research done. We will have a paper presented at ISC, so that's why I didn't include any of these results here. So we have that version coming. Then we are continuously looking for all these newer optimizations, the new CUDA support, as well as Intel MIC has this new night landing which is coming up, so we are working towards that. How do you take advantage of this collective offload framework, topology aware collectives, power aware, so all these directions we are continuously working, and you will see from our group's point of view what we do is like we first carry out the research, that is our basic goal, and we evaluate different design alternatives and then try to push it into the open source version so that you people can actually take advantage of it. So that's what we have been doing for the last 14 years and we'll continue to do. Now the next part, let me take another 5 minutes just to focus on the big data side. So this is where all the scientific side is happening. Now if you see on the big data side, of course there is a lot of discussion happening on the how do you work on the data. There are all different kinds of data with 3 different properties: volume, velocity, variety, as well as people have added now value and veracity. So what we started doing here around 3 years back, we saw that all these middlewares, they are still using sockets, they are still using Ethernet. Okay, so they are still like lagging behind. So what we asked the question that what are the challenges if we want to try to use the high performance networks? What will be the challenges? What will be the bottlenecks lie? And just like what we have done for MPI, can these bottlenecks be alleviated with new designs? And the other thing is, can the HPC clusters themselves be used for big data? So currently if you see people are using Hadoop, these are kind of different machines, different clusters, whereas the HPC clusters are just sitting there is no connections between these. So we try to take a look at both, and our initial focus has been on Hadoop, HBase, Spark and Memcached. So here again the challenges are very similar. Like the previous slide I showed, but what we try to do is trying to first ask the question that can we change from the sockets to RDMA? What will be the challenges if all these middlewares we want to move? And then of course if we can do that and we see some benefits which I will show you, can we even make upper level changes, because all these middlewares were written with slow network in mind. So now if we can make that operation, low level operation faster, then the upper level designs can also be modified. So this is the standard Hadoop environment. Many of you might have seen like MapReduce, HBase, HDFS. So that is the underlying component, and then the MapReduce is the model. So here we started working on both the things, like saying all components of Hadoop, let's say HDFS, MapReduce, RPC, HBase, etc., can they be rewritten with native InfiniBand verbs? Okay. And if it can be done, then the Hadoop applications can take advantage of it. And the second direction is just to take MapReduce, because many people don't want to even touch HDFS or something. They want to use MapReduce. So the question is, can it be run on HPC cluster with existing file system like Lustre? Okay. So we have actually worked on this. We are continuously making releases. So one is the RDMA for Apache Hadoop project. So if you go to this place, you can actually download our version. So here we have actually converted HDFS, MapReduce, RPC, all these things into RDMA, and then trying to put them together, and I will show you some performance numbers here. So let's say just this HDFS. If we take the HDFS, so this result was presented at SC 2012. So here you will see like this is comparing 10 gigabit and then the InfiniBand QDR, but here you can, this is running over IP over IB and this is running with the native IB. So here you can see that compared to InfiniBand, IP over IB, you can get almost like 30% improvement. This is a test DFS IO, which is a common benchmark again for SDFS RDMA. So here you will see that similar kind of things. This is the throughput, so you can increase by 24%, or here you can increase by 61%. The same thing happens also MapReduce. So we have taken the MapReduce paradigm and then converted into native InfiniBand. And so here it is comparing 10 gig IP over IB, and also there is another package from Mellanox, the UDA, and then we are comparing that with our version. So here you can see similar kind of things, you get like 41%, 52% improvement compared to the IP over IB. Then, so those are on smaller clusters. We have taken this design to larger clusters. So this is running on a larger cluster with different data sizes on a 240 gigabyte sort over 64 nodes. You can see like you get 40% improvement compared to IP over IB. This is on the TAG Stampede on 64 nodes. So this is like 1,000 cores. You get around 38% improvement. So then the second direction, which I said, if people just want to use MapReduce and Lustre, not HDFS, can they really take advantage of this? So here we have done some preliminary designs. We'll present this at a Europar in August. And here you will see that there are two solutions. That means, let's say Stampede has both. They have local disk, they also have Lustre. Okay. So here it is trying to show that the local disk is used as the intermediate data directory. So then you can get around 44% or 48% improvement. The second solution is actually the Lustre is used as the intermediate data directory. You don't touch your local disk. So here again you see around 35 to 33% improvement. So then very recently the Spark architecture has come. This is for new in-memory computing. So not just you are doing I/O, you are also trying to do this computing. So here these are very new results. We just got it last week. So I am just trying to share here. So this is the first RDMA design of Spark over native InfiniBand. And here you will see like there is an application in the Spark domain called group by. So here you will see like just on 4 nodes, 8 nodes, we have not gone to more than 8 nodes yet. You can see just 18-20% improvement just by changing from IP over IB to the native InfiniBand. Now I know Brian is showing me the time, so I will skip this Memcached D, but that is again a Web 2.0 architecture for big data. We have done similar kind of things here. So broadly, to conclude the presentations, what I demonstrated here that both InfiniBand and all these RDMA features are gaining momentum in the HPC systems, and as we continue to move to Exascale, we need to look for this kind of newer solutions. And I demonstrated how MVAPICH2 and MVAPICH2-X can give you benefits, and the same thing also needs to be done for the big data domain. So these are our all standard sponsors, but these are all my heroes. Okay, I just come here and talk, but these are all the past and present students, staff who do the hard work. So I just want to acknowledge all of them. Without their support, hard work, we could not be doing this kind of projects. And more importantly, another thing I just want to share with you, since last year, because a lot of people are using MVAPICH stack, we actually created an annual user group meeting called MUG. So this year again we will try to continue that. So this will be held in August. So these are all the speakers lined up so far with keynote talks as well as several speakers from all over the world. We also have a call for presentation, contributed presentation. So if you have some good applications, good designs, or using MVAPICH2, MVAPICH2-X, trying to show how you are getting the benefits. So we want to bring you to this MUG meeting so that you can share your experience. So if you have something, please feel free to submit. And we will also have a half-day tutorial on MVAPICH2, MVAPICH2-X and MVAPICH2 optimization and tuning. We are getting a lot of requests as systems are becoming complicated. People exactly want to learn which parameters to change. So we have come up with a half-day tutorial, and that's what we'll be giving. So if you just want to learn those things also, you are welcome to attend. And last but not the least, I'm always looking for very bright people. It's a advertisement I'm trying to do. If any one of your student or something want to come, or professionals as scientists or engineers, please feel free to let me know. So with this, let me stop here. If there are any quick questions, I can handle it now. Otherwise, I am here throughout the day, and I'll be very happy to discuss with you. Any quick question?
Will your slides be available?
Yes. I think these guys are there. In another 5 minutes, you will see all the slides available. No? 50 minutes.
Thank you.
Okay, thanks a lot.